Okay, so after that example involving application of the mass balance, and remember the mass balance for an open system was derived by applying the Reynolds transport theorem to conservation of mass. So after that two examples we had there for mass conservation for an open system, let's shift gears to the more important and more interesting application, which is conservation of energy for an open system. So energy balance, E-balance for an open system. So let me show you what such an open system might look like, and I'll draw and show you what possible energy interactions there might be. So we could have this weird generic system with all these inlets and outlets. So we have all these inlets and outlets. Okay, so we got mass flowing in. Maybe this is inlet port number 1. So m dot in 1. Maybe this is inlet port number 2. So we have m dot in 2, all the way down to however many inlets we have. Same thing on the outlet side, we have mass flowing out. So this is m dot out 1, m dot out 2. All these mass flows out of my system. And here's the control volume for my system. It's clearly an open system. We got mass crossing the system boundary at various locations. So that is my control volume or my system, okay? So we have all these inlet flows and all these outlet flows. Okay? Now remember from our discussion of closed systems, there are various kinds of energy interactions that occur. There's work and there's heat. So I could be adding heat to my system, Q dot. I could also be doing work on, or the system could be doing work. So I could have a propeller here with some W dot shaft going on. So this guy could be turning and delivering power at a rate of W dot shaft. I could also have some wires in here. Okay, I could have some wires in here, and that could be the positive and negative lead, and therefore I can have some W dot electric, can barely write it down there, W dot electric. And that would be work on the system, okay? Pass a current through the wire, you're doing work on the system as it's being dissipated through a resistor. Let's see, so there's shaft work, electric work, boundary work. We could have a piston in here. We could have a piston, okay? And this piston could be moving up or down. So I could actually have a piston on the boundary of my open system, and it could be moving up or it could be moving down, changing the volume of the system, and therefore doing boundary work. So I could have W dot boundary as well, okay? I could have W dot boundary. 3 kinds of work: electric, shaft, and boundary work. All can be present for my open system. Okay, let's write the Reynolds transport theorem here. Now that we have an idea of what our system may entail, mass flows across the system boundary, various kinds of heat and work interactions. So the Reynolds transport theorem says what? It says the change of beta time rate of change of beta within my closed system is equal to the time rate of change of beta within my control volume with respect to time, plus the sum of m dot lowercase beta out minus the sum of m dot lowercase beta or lowercase b in, summed over all inlets and outlets. Okay? So those are Reynolds transport theorem. We derived that during the previous lecture, as I recall. All right? Now, in this case, if you go back and look at that chart we had a long time ago, I think it was in the last lecture, if we apply this to energy, what we're saying is beta is equal to total energy, lowercase b is equal to energy per unit mass, so that's lowercase e, and the time rate of change of energy within my closed system, d beta closed system, dt, in this case, beta is equal to total energy, dE dt, is equal to the heat added minus the work done. So you go back and you look at that table we had where I had different values for beta, and I had the closed system energy and mass balance. You'll see these terms in that table, okay? Okay, so let's plug in. The change of beta within my closed system is really the time rate of change of total energy within my closed system. And that's equal to Q dot minus W dot. So that's my closed system energy balance right up here. This is my closed system energy balance. Change of beta within the closed system. Beta is energy. So this is change in total energy within my control volume with respect to time. And lowercase b becomes energy per unit mass, so I have the sum of m dot e out, and this one becomes the sum of m dot e in. Okay, so that's what those terms become when I have the energy, when I apply it to total energy E. Apply it to total energy E. Oop, looks like my microphone cut off. I think we're going to stop.